Good afternoon, good evening, and good morning, everyone. So my name is Yi. Thanks for taking your time to join my session. So today I would like to talk about the non-parametric optimization on the in-machine. So the optimization for electrical machine is always an interesting and challenging topic. So during optimization, you may have different level of skills you want to achieve. Maybe at the very beginning, you just want to maximize your torque. And afterwards, you may be okay. We have achieved the maximum torque, and could we also reduce the weight because it will also reduce the production cost. And finally, if you have almost finalized design before production, you may also want to say, okay, if the harmonic can be surprised, so it will relevant to the drive comfort. So let's say if at beginning we want to maximize the torque, so the normal parametric optimization will be somehow sufficient for this workflow. And then I take this machine as an example. So this is a V-shape buried permanent magnet synchronous machine. It has 8 poles, 48 slots. And if we assume that the maximum current density would be 18 ampere per millimeter square, so the maximum current will be around 670 ampere. And then operating point would be like 3/3 from the maximum, and then it will be around 446 ampere. So for this optimization, for parametric optimization, we focus on the rotor, and we try to parameterize some parameter, and then the stator will be keep unchanged for this workflow. And then we focus only for W3, W4, and alpha. So because we want to assume that maybe the size of the magnet will keep unchanged, we just want to slightly change the gap around the magnet. Okay, so how does the optimization look like for the parametric optimization? So let's say we have initial design, and for the initial design, we have the alpha W3 and W4 with 15, 2, and 3.5. So with the parametric optimization around 100 steps, we can somehow get the optimized design. So during optimization, let's say we set the alpha from 10 to 20, W3 from 0.5 to 6, and W5 from 1.5 to 5.5. And somehow after 100 steps, we find the optimized design around 59 steps. So this is how our optimized design look like. For sure, we have a new set of the alpha, W3, and W4 with 16, 6, and 5.5. So here we want to verify or confirm that we really have an improvement from parametric optimization. So we do a load angle sweep on the same current. You can see that for the initial design, the maximum torque happens on the load angle with 41.53, and then the maximum torque is around 240 Newton meter. If we see the optimized design, we see a little bit shift on the optimal load angle. So, and also the torque is increased to the 264. So in a short summary, with this parametric optimization, we finally get a 10% torque increase. And then if we check in this counterplot, we can see a better overview that not only for this single current, but also in the other kind of current, we increase average torque. So somehow if we check this red region, we can see that in the optimized design, the red region is expanded. So we have the better torque performance. But unluckily for the 6 harmonic, we have the bad performance compared with the initial design, but speaking to the 12 harmonic, so we have reduction, so we have a more blue region. So this is for the parametric optimization, so it's nothing special. So from the initial design, we use the parametric optimization, we optimize the torque, we get an optimized design. But this time, if let's say, if I want to reduce the weight, how should I do? So maybe the non-parametric optimization would be the approach here. So I guess maybe you have heard this phrase or this phenomenon several times before, maybe like for my colleague Tunis, he has introduced its application in the high frequency domain. But now today, I would like to focus on low frequency domain, like for the optimization of the electrical machine. So how this non-parametric optimization used for the electrical machine optimization, like we can use the topology optimization to reduce the weight. So topology optimization is generally called the conceptual design optimization. So the purpose is for sure to find the optimized structure, and we have the design space. For this design space, this can be either a sheet or volume. And then in the hub of this design space, we fill two materials, the material 1 and material 2. And then we see as a field with which one, we will have a better performance. So like for electrical machine, we may have the material 1 with iron or steel and material 2 with the air. And before really we set up the topology optimization, we have to do something slightly preparation for this. So maybe you have noticed that we optimize the rotor, nothing special, but we add a small shaft ring. So this shaft ring will guarantee the connection between the optimized rotor and the shaft. So we have to somehow do some manual work, but that's all. And then besides that, we let the rest of the part as a design space. So this is the red region. And then for this red region, we see topology optimization. Therefore, we fill the material either with steel and air. And maybe you also notice that this is rotor. It has some symmetrical constraint or condition. We would like also expect the left part will be symmetrical to the right part. So we need to set the symmetrical constraint here, and then we actually optimize only maybe the left part. So the right part should be the same as from the left. So after defining the design space, we need to know what goals we want to achieve. So like this way, we want to reduce the torque, reduce the weight. So the minimized string energy would be the best choice. Like this is for stiffness optimization. In the meantime, because you maybe also observe that from the parametric optimization, if we change the design, the best optimized load angle is also slightly changed. So for this optimization, we don't specify any load angle. So we just say, okay, we just want to make sure that this machine working in the motor range. That means from 0 to 90 degrees on a fixed current. And then we want to let the optimizer tell us for this candidate design, what is the best optimized load angle. So we don't set it, we just set a range here. And then we are expecting also from the different candidate design, we have different optimized load angle. And for this topology optimization, we want to reduce the weight for sure. But how we can reduce the weight, I have no idea. Maybe we need to fill some holes, opening and slits. I would like to let the optimizer tell me, okay, in which region I need the holes, in which region I need the opening or slits, and so on. So this is something I'm expecting from the optimization. And then we reduce the weight, but we don't also want to lose too much the mean torque. So we can expecting somehow little bit increase as on the torque. So the initial design is 264. Maybe for the new design from the after optimization, we hope could be beyond the 265 Newton meter if it can achieve. The last thing is from the structure side. So if the machine, we want to take the Fermi stress into consideration. That means if the machine runs in the maximum speed, like the 15,000 RPM for this machine, we don't want the rotor, for example, tear up. So let's say in this case, we set the 300 megapascal for the rotor lamination or for the rotor main part, and 100 megapascal for the magnets. Okay, so that is how the optimization look like. You see the region is changing, and then the blue region is some region we want to reduce, and the red region is we want to keep. So we somehow find the optimal design. Maybe you can see that in the 78 steps. So this is how the process look like. So the string energy is somehow describes the torque reduction, the goal achievement. So we are struggling at the beginning, but maybe I switch to my pointer. It's struggling at the beginning, but then falling down in the end. And then for the weights, and we are always below the 6% around. And for the mean torque, we somehow maintained in the desired weight range. And also from structure side, so either rotor lamination or magnets, we are all below the limit, like 300 megapascal for rotor and 100 megapascal for magnets. I would also want to mention that, so this optimization has the 67 iterations. So it will finish in 1 hour because we only optimize torque. So maybe one of the 6 period will be enough. What does this mean? This means after 1 hour, you will get an optimized design from topology optimization with a much reduction on the weight. So this would be the benefit of the most charming thing for this topology approach, for this non-parametric optimization approach. It looks like the last design, the best design because it's falling down in the lowest part. But will that really be the best design? It really depends. So if we really look into details, so this the first one is initial design, the last one is the last design. So if we check this region, so the red region, we can see that. So for the last design, for the initial design, where there is some support to fix the magnet in the rotor, but in the last design, we are losing such kind of support. So maybe it is benefit or it is good for the weight reduction, but it's not that good for realistic production. Therefore, we need to compromise somehow. So we pick the 46 design. So this means we have the torque, we have the weight reduction. In the meantime, we still maintain the support for the magnet. So this design will be used further for the optimization afterwards. Okay, so we compare the results again from initial design to the optimized design. So we sweep the load angle. From initial design, we can see that, okay, around the 46 degree, we will get the maximum torque around the 264. And then from optimized design, well, the load angle change from 40, it is expected, but the torque is reduced to the 253 Newton meter. So it is not that good that we have around 4% reduction from torque, but the good thing is we have a 30% reduction for the weight. So speaking to the structure side, so we can also obviously see that even if in such kind of reduction, we didn't lose the strength of the rotor. So that means we still have the magnet is still under the 100 megapascal limit, and the rotor is under 300 megapascal limit on the maximum speed. That means we try to make full use of the region of the part of the rotor, and then just leave out the useless part. So okay, let's make a short recap. So we use the parametric optimization to find the optimized design to maximize torque, and then we use topology optimization to reduce the weight to get the optimized design. So what if I want to surprise harmonic? And then in this case, we can use the shape optimization. So shape optimization is usually used for the fine-tuning design. What does this do? It will try to push your current design to a wider or to other limits, to higher limits, and then that means you have the design space, but this time this must be a surface area. And then the green part or green node is the design node you want to move. And then during shape optimization, you move the green part or the green nodes inside and outside, and then you will find the optimized design. So for our design now, for example, if we want to, we can set up the design for the stator firstly. So for stator, we try to make, for example, optimize the teeth. Or the teeth could be the front face and also the side face. So this is the red region you see. And maybe you also see that for the teeth. So we have, for example, 48 teeth. After optimization, for sure don't expect we have the 48 individual teeth geometry. So we should have set some geometry constraint here. So like we can set the rotational cylindrical geometry. That means, okay, for sure we have 48 teeth, but 48 teeth should have the same geometry. So that means we only optimize this green part, and the red part should follow the green part. And in addition, we also want to say, okay, the teeth should have the left part and the red part. They should be also symmetrical to each other. So we only optimize the purple part, and the green part should be the same as from purple part. How far should I move the nodes? So we need to define some shape constraints, like it grows to outward from 0.1 millimeter and shrink inward from 0.4 millimeter. To give you a feeling how big it is, so the magnetic air gap is 0.7. So that means we are really careful to move the nodes into the air gap, but we are very aggressive to move the nodes away from the air gap, so with 0.4. So that is enough for the stator design setup. We are jumping to the rotor. So similar like a stator, we still have the symmetrical constraints. So that means the left part should be the same with the red part. And also for rotor surface, so maybe you have to see that this is the blue part. So we have the zero growth, maybe the 1 millimeter strong shrink for this part, for this rotor surface. And for the rotor gap, so this is will be the green part. We have the grow and shrink with 0.8. And for the other parts, this yellow part, maybe they are not really help to improve my performance. But what I expect is from this strip optimization, I want to smooth the surface from this kind of, from this surface, because from topology optimization, the surface may be somehow discreted. And then after shape optimization, I'm expecting a smooth a smooth surface connection in each region. Maybe you also notice that the rotor surface and the magnet gap are really moving aggressively. So they can even almost touch with each other. So it will be fun for the optimization because it doesn't care about production. But it's not acceptable for the production, because if the rotor and the rotor surface and the magnetic gap are approaching too close with each other, we get a very thin panel. And this very thin panel will have the stress problem, and then it will maybe tear up in the end. So to get rid of this case, we can also, for example, define the minimal distance between the rotor surface and the magnetic gap, like 0.55 millimeter. That means no matter how far or how aggressive the optimizer moves the rotor surface and magnetic gap, the minimal distance should be maintained at 0.55 millimeter. It should not be exceed. Therefore, we will fulfill the stress constraints. And then we are speaking to which kind of operating point we want to optimize. So this is a torque speed curve for this machine. And then there are too many possible operating points. And then for this optimization, we maybe pick some particular or specific or special operating points. So we pick the first one with maximum torque, and we pick second one with maximum speed, and we pick the third one with the maximum efficiency. So that means for the common optimization, we try to optimize these 3 operating points simultaneously. And then what is good for this optimization? We can, for example, because the main goal is we want to suppress harmonic to improve the drive comfort, then the torque ripple reduction will be very important. And also the positive mode ripple reduction is also important. So no matter for which operating points. And then during optimization, we will know that, okay, I know the torque will be reduced somehow, but I don't want to reduce too much. I can say, okay, for the first operating point, so this is the one with maximum torque. We said, okay, maximum reduction 5%. But for other two, maybe we can give the better condition, like the 10% reduction. It is allowed. And for the fundamental mode ripple, we want to achieve the 50% reduction in all operating points. So maybe at this time you are a little bit confusing what is positive mode and what is fundamental mode. So all the thing is from the two-dimensional Fourier transform in lumped forces. So we expand the lumped forces in 2 dimensions. One is time, one is space. That means in different time, in different space or position, you have different lumped forces. So this is how this spectrum look like. And then if we come back to this formula, we can see that, okay, the positive mode is actually the DC value from this Fourier transform. That means the position independent. So it's only time dependent. That means no matter where you are, in which position of the rotor or stator, they are always acting with the same amplitude. This is called positive mode. And then the fundamental mode is just first order from Fourier transform. Why this order so important? Because in the structure side, maybe some specific mechanical order will result some resonance. If we want to improve the comfort, we need to reduce resonance, and then we need to reduce some specific mechanical order. So here is just an example that we can optimize the specific mechanical order. And also we need to follow the structural word. So maybe it's 250 megapascal should not be exceeded from rotor on the maximum speed. Okay, before the simulation, CSC has also a really nice feature that can predict which region would be the hot region for your optimization. So here I give you an example. If we want to optimize the mean torque, we can see that, okay, the almost the upper part will be important. The lower part, it has less influence. And no matter stator teeth and also rotor surface will be important. But if we check the ripple, so if we check the ripple, we can see that the teeth of the stator ripple of the stator will be much important than the rest of the region. So let's say if we want to have a better ripple performance, we are expecting some change from the stator teeth. Okay, so this is how does this optimization look like, because it is a fine-tuning optimization. Compared with topology optimization, we don't see some really big change, but we still can see some movement from this colorful region. Maybe from here you can see that we have the surface is no more smooth, and also the hose is trying to close in the very end. So we have the around the 59 steps in the end. So it is really a little bit longer simulation. We finished with 10 hours. The reason is not like topology optimization, we only care about torque. For this optimization, we care about lambda forces. For lambda forces, we have to simulate with full period. We cannot simulate with 1/6 of period. So this will increase the simulation time. And besides this, we simulate or we optimize 3 operating points simultaneously. That means we have 3 times 50. We have to run to simulate each operating point individually. So this will be for each iteration, we have 3 times a simulation. So this will also increase the time, but it's still acceptable. That means after one night, you will get the optimized design from ship optimization. So let's check how good it is. So we want to minimize the torque ripple. So no matter for each operating point, OP1, 2, 3, we can see the falling down curve. So we have the good torque ripple reduction. And also we want to minimize the positive mode. That's also good. We have a good reduction compared with initial design. So how about the torque look like? So if I check the mean torque, we want to say only the OP1 have only 5% reduction and the other two with 10% reduction. So we can see that maybe it's not that clear. So the first 2 lines is the the green and blue. They are this one. So they fulfill the limit. So let's see, the OP1 is 5%, it's fine, and the blue one is OP3, we have 10%, it's also fine, but not for the case for the purple. So it is a little bit exceed the 10%, so it's not that good. For the fundamental design, we try to reduce the 50% reduction, but now the optimizer is still trying to reduce, but it's too difficult for the optimizer. So it stops in the end. Maybe in the next time we can give more freedom to the ship optimization, like we can increase how the range from the node movements. Like before we can allow the 1 millimeter move, now we allow 2 millimeter move. And then from stress, we still not that really achieved, but compared with the initial design, we can see that the last design still has a reduced structure, the stress. Okay, so what happened? Okay, so this is initial design, this is our optimized design. Maybe it's not really good to observe, so let me zoom in. So you can see that the initial design have very smooth rotor surface, but the optimized design, maybe it's more obvious. So the rotor surface is no more smooth. So it has some changes. So the optimizer really do something here. And then if we check, okay, we have the 3 operating points, and then we plot this in time domain. We can see that operator 1, 2, 3, we try to minimize the torque ripple. We try to maintain the mean torque, and then so we can first see that the oscillation from each operating points are smaller. So the gray dashed line is our reference from initial design. So the colored one is from optimized. So also the oscillation is for sure reduced. So for this one and for this one, the mean torque is somehow maintained, but not for this one, the OP2. So we have no before. And also we want to minimize torque ripple. So for sure, the gray dashed one have the big oscillation, and the color one with less oscillation. Also for the fundamental mode, yes, we have also the less oscillation. And then let's compare to the real value. So for the torque ripple, we have average around 50% reduction for all operating points. And for the positive mode, we have maybe better 55% as average. And for the mean torque, well, it's not that good because OP3 and OP1 and OP3 we achieve the goal, but OP2 we are slightly exceed. So 10% as requirement, but we are landing with 12%. And then for the fundamental mode, no, it's not that good. We all of them didn't achieve, but we can see that the average is still around 30% reduction. So here is the stress, how look like. So this left one is initial design and the right one is optimized design. Because chip optimization is fine tuning, so you don't really see the much difference from the stress distribution, not like from topology optimization. But from this plot, you can still see that compared with initial design, the last design still have the less stress than before. Okay, so if you still remember, for this chip optimization, we are only operating these three operating points, but the machine could be operating arbitrary operating points. So how does it look like? So we plot again. So we show the machine with different current, with different load angle. So with our operating points, we can see that, okay, that was good. So even if we operate these three operating points specifically, we get the reduction in almost all the operating points. The more good thing is if we plot the operating points with maximum torque. So this is a white dot. That means on the wrist current, we get the maximum torque. We can see that this also lies almost in the blue, in the deep green region. That means in the most efficient operating point, we still have a very good torque ripple reduction. So this is the benefits as on from chip optimization. You optimize three operating points, but you get the benefit from the whole operating range. So let's make a wrap up again. So we have initial design. We want to maximize torque. We use parameter optimization. We get the optimized design. And then in the meantime, we want to also reduce the weight. We go to topology optimization, and then we have the optimized design from topology optimization. And in the end, we want to surprise the harmonic, and then we use chip optimization to do some fine tuning, and then we get the finalized design. So it's really a long journey from parametric to topology and to chip. So from parametric to non-parametric optimization. But how is the performance is really look like in the end? So we again compared the initial design from this stage, from first step, and the optimized design from the last step. So we compare the weight, mean torque, torque ripple, positive mode, and fundamental mode. So what we can see that, so the weight compared with initial design, we have 30% reduction on the weight. We have also good, not that good, but still have the increase on the mean torque. But also in the meantime, we reduce the torque ripple around 70%, and the positive mode with 50%, and the fundamental mode with 35% reduction. So this will strongly improve the drive comfort. So this can be expected. Okay, so that is bring to my last slide. So if you have questions, please let me know.